Imagine a candle burning alone in a dark room. Its flame trembles above the wick, sending light across the walls and warmth into the surrounding air. Slowly, the candle becomes shorter. Wax is consumed, gases drift away, and after enough time, the flame finally disappears. The room becomes dark again. Hours later, even the warmth seems to be gone. If you entered the room then, you might find almost no obvious trace of the energy that had once filled it. The light is gone. The heat has faded. The flame no longer exists. Yet according to one of the deepest principles in physics, none of that energy was simply erased. It changed, spread, and became difficult to recognize, but it did not simply vanish. We learn this idea so early that it can sound almost ordinary. Energy cannot be created or destroyed, only transformed from one form into another. A battery loses chemical energy while producing electrical energy. A falling object converts gravitational potential energy into motion. Friction turns organized motion into heat. A star converts nuclear energy into radiation that can cross enormous distances through space. In a classroom, these transformations can be written as neat equations. The energy before an event is compared with the energy afterward, and everything balances. But the simplicity of the equation hides a strange question. If energy never disappears, where is all the energy from everything that has already happened? Think of a sound fading into silence. When someone strikes a bell, the metal vibrates and pushes against the surrounding air. Pressure waves travel outward until they reach your ears, allowing you to hear the tone. Eventually, the bell becomes still and the sound disappears. But the energy carried by that sound has not fallen out of existence. The vibrations spread through the air, strike walls and objects, and are gradually converted into tiny amounts of random molecular motion. The room becomes warmer by an amount far too small for you to notice. What began as an organized vibration becomes scattered among countless particles. The same thing happens when you slide a book across a table. At first, the book has obvious kinetic energy. It is moving, and you can see that motion directly. Friction gradually slows it until the book stops. It would be easy to say that the motion's energy has been lost, but it has merely changed form. The surfaces of the book and table become microscopically warmer. Molecules vibrate a little more intensely. Some energy becomes sound. Tiny deformations occur in the materials. The clear, organized motion of one object has been distributed into movements so small and chaotic that your eyes can no longer follow them. This distinction is essential. Energy can still exist even when it is no longer useful or visible. A charged battery contains energy in a form that can be directed through a circuit. Water behind a dam has energy that can turn a turbine. Fuel contains chemical energy that can drive an engine. These are concentrated forms of energy. They can produce noticeable change. But after that energy has been used, much of it eventually becomes dispersed heat. The quantity has not simply disappeared, yet recovering all of it and concentrating it again can become practically impossible. Now imagine following this process much farther. Sunlight arrives at Earth carrying energy that originated inside the sun. Deep in the solar core, nuclear fusion converts hydrogen into helium. The resulting energy moves outward through the sun and eventually escapes from its surface as radiation. Some of that radiation crosses roughly 150 million kilometers of space before reaching Earth. A photon from the sun might be absorbed by a leaf. Through photosynthesis, its energy can contribute to chemical processes that store energy in molecules. Later, an animal may eat the plant. Those molecules are broken down, and some of their stored energy contributes to movement. The animal walks. Its muscles generate heat. That heat spreads into the environment, and Earth eventually emits energy outward as infrared radiation. The original energy has changed identity again and again. Nuclear processes became radiation. Radiation contributed to chemistry. Chemistry contributed to motion. Motion became heat. Heat became infrared light escaping toward space. At no moment was there a tiny glowing substance called energy being passed from one object to another. Instead, energy was a property, carried by different physical systems as they changed. That is an important point because energy is often imagined as though it were a material ingredient. We speak of objects containing energy, using energy, or running out of energy, and these phrases are useful. But energy itself is not a substance that could be poured into a container. You cannot open an electron and find energy hidden inside it. A photon carries energy, but energy is not a smaller object inside the photon. A moving object possesses kinetic energy because of its physical state and motion. A system can possess potential energy because of the relationships between its parts. Energy is better understood as a fundamental physical quantity that remains connected across transformations. This raises a subtle mystery. If energy is conserved, why does the world seem filled with processes that only happen in one direction? A hot cup of coffee cools down. It does not normally absorb random heat from the room and spontaneously become hotter. Smoke spreads through the air instead of gathering itself back into a neat cloud. A shattered glass remains shattered. Sound fades rather than assembling itself from random molecular motion into a perfectly organized wave. In each case, energy remains accounted for, but something about the organization of that energy changes. The universe seems to have a preference for spreading energy out, and once energy has spread, it becomes harder to use. This is why conservation of energy does not mean that everything can continue forever in the same form. A star can exhaust the nuclear fuel available in its core, even though the energy involved has not vanished from the universe. A machine can stop moving, even though its kinetic energy became heat. A living organism constantly requires usable energy because energy that has already been dispersed cannot simply be gathered back together without other changes occurring elsewhere. The amount of energy and the usefulness of energy are not the same thing. That distinction will eventually lead us toward entropy and the arrow of time. But before we reach them, there is an even stranger layer to the story. Why is energy conserved at all? It might seem natural to say that conservation is simply a rule of the universe. Nature keeps its books balanced because that is what nature does. Yet modern physics reveals a more beautiful connection. Conservation of energy is deeply related to a symmetry of time. Imagine performing an isolated experiment today. Then imagine performing exactly the same experiment tomorrow under identical conditions. We expect the fundamental laws to be the same. An electron does not behave differently simply because the calendar has changed. Gravity does not suddenly acquire a different law on Tuesday. The basic equations of physics do not appear to depend on when we choose to perform the experiment. This property is called time translation symmetry, and through Noether's theorem, one of the most profound results in theoretical physics, this symmetry is connected to conservation of energy. Very roughly, when the laws governing a system do not change with time, there is a corresponding conserved quantity, energy. So energy conservation is not merely an isolated accounting trick. It is connected to the uniformity of time itself. That connection makes the original question much stranger. When we ask where energy goes, we are also approaching questions about why physical laws remain consistent from one moment to the next. Energy, change, and time are woven together far more deeply than everyday language suggests. And perhaps that is the most interesting place to begin our journey. A candle goes out, yet its energy continues into the room. A sound disappears, yet its energy becomes microscopic motion. Sunlight reaches a leaf, becomes chemistry, movement, warmth, and radiation. Across the universe, energy continually changes form, while the structures carrying it appear and disappear. What we experience as an ending is often only a transformation we can no longer follow. The flame vanishes, the sound becomes silence, the motion stops. But underneath these quiet endings, the physical story continues. And if we want to understand where energy truly goes, we must next understand why it spreads, why concentrated energy becomes harder to recover, and why a universe that conserves energy can still slowly move toward a state in which less and less can happen. If energy never truly disappears, then one of the strangest things about the universe is how quickly it becomes difficult to use. A cup of hot coffee left on a table slowly cools. The warmth passes into the surrounding air, then into the table, the walls, and everything else nearby. Eventually, the coffee reaches almost the same temperature as the room. The energy that once made it noticeably hot still exists, but it has become spread across a much larger environment. Nothing has violated conservation of energy, and yet something important has been lost: the ability of that concentrated energy to produce an obvious change. This happens everywhere. A spinning wheel gradually slows because friction transforms its organized motion into heat. A bouncing ball rises slightly less after each impact as energy spreads into sound, deformation, and microscopic motion. A fire burns brightly for a while and then fades as its stored chemical energy is redistributed into radiation and warmth. In every case, energy survives. What changes is how concentrated and organized it is. This is where the idea of entropy begins to appear. Entropy is often described simply as disorder, but that description can be misleading. A better way to approach it is to think about the number of microscopic arrangements that can produce the same large-scale situation. Imagine a container divided into two halves. All the gas molecules begin crowded into the left side, while the right side is completely empty. If the divider is removed, the molecules begin moving throughout the entire container. After a short time, the gas is spread approximately evenly between both sides. Nothing prevents the molecules from moving back into the left half. The laws governing their collisions work just as well in either direction. In principle, every molecule could happen to move left at the same time, recreating the original state. But for a large number of molecules, the probability is unimaginably small. There are vastly more ways for the gas to be spread throughout the container than there are for every molecule to be gathered into one half. The spread out state therefore has higher entropy. This statistical tendency is so overwhelming that it appears to us as a law of nature. Gas expands, heat spreads, perfume released into a room diffuses through the air. These processes do not normally reverse themselves, even though the microscopic laws of motion do not simply forbid the reverse sequence. The reason is not that nature contains a mysterious force pushing everything toward chaos. It is that high entropy arrangements are overwhelmingly more numerous than low entropy arrangements. Imagine dropping a single grain of sand onto a table. There are many places it could land. Now imagine dropping millions of grains and demanding that every one of them accidentally form a perfect castle. The laws of physics do not necessarily prohibit such an arrangement. It is simply buried among an incomprehensibly larger number of arrangements that look nothing like a castle. Energy behaves similarly when it spreads through matter. Suppose one corner of a metal bar is heated. The atoms in that region vibrate more intensely. Through interactions with neighboring atoms, energy begins spreading along the bar. Eventually, the temperature becomes more uniform. The total energy remains present, but there are enormously more microscopic configurations corresponding to energy being distributed throughout the bar than configurations in which nearly all the thermal energy remains concentrated in one tiny region. So the system naturally evolves toward the more probable condition. This is the heart of the second law of thermodynamics. In an isolated system, entropy tends not to decrease. Energy remains conserved, but its distribution tends to move towards states that are statistically more probable. And this explains something that conservation of energy alone cannot explain. Imagine two objects, one hot and one cold, placed in contact. Energy flows from the hotter object into the colder one until their temperatures approach equilibrium. Conservation of energy tells us how much energy one object loses and the other gains. But conservation alone does not tell us why the process has a preferred direction. Why does heat flow from hot to cold, rather than spontaneously concentrating itself in the hotter object? Entropy provides the missing piece. The state in which energy is more evenly distributed corresponds to vastly more possible microscopic arrangements. The reverse process is not impossible in the same absolute sense that an object cannot exceed certain physical limits. Instead, for ordinary macroscopic systems, it is so extraordinarily improbable that we effectively never observe it. This gives energy a curious double life. On one level, it is conserved with extraordinary precision. On another, its usefulness continually changes. A quantity of energy concentrated in one place can perform work. The same amount spread almost uniformly through the environment may be practically useless. Consider the ocean. It contains an enormous amount of thermal energy because it contains an enormous number of moving molecules. Yet you cannot simply place a machine in water at a uniform temperature and extract unlimited useful work from that thermal motion. To continuously obtain useful work from heat, you need a temperature difference. There must be somewhere hotter and somewhere colder so that energy can flow between them. Differences are what allow things to happen. A battery works because there is a difference in electrochemical potential between its terminals. Wind exists because solar heating helps create differences in temperature and pressure within the atmosphere. Hydroelectric power works because water begins at a higher gravitational potential and can move downward. Engines operate by exploiting differences in temperature or pressure. Stars shine because their interiors contain enormous gradients and ongoing physical processes capable of releasing energy. Where there is no difference, there is nothing to drive the change. This is why the spreading of energy matters so deeply. As differences disappear, the ability to perform useful work decreases. The coffee cools because its temperature differs from the room. Once the coffee and room reach the same temperature, the obvious flow of heat stops. The energy is still there, distributed among molecules, but the temperature difference that could drive further change has largely disappeared. The universe is filled with temporary differences like these. Stars are hotter than the space surrounding them. Planets receive concentrated radiation from stars and emit lower temperature radiation outward. Chemical systems contain molecules far from equilibrium. Living organisms maintain intricate internal structures by constantly taking in usable energy and releasing more dispersed energy into their environments. Life itself depends on energy not yet being evenly distributed. A living cell is not an isolated object calmly sitting at equilibrium. It constantly exchanges matter and energy with its surroundings. It maintains gradients across membranes, constructs complex molecules, repairs structures, and performs chemical work. None of this violates the second law because the organism is not decreasing the total entropy of an isolated universe. It maintains local organization while increasing entropy elsewhere. The same principle applies to almost every organized structure we see. A refrigerator creates a cold interior, but only by consuming electrical energy and releasing more heat into the room. A city maintains its complex organization by consuming enormous flows of energy and producing waste heat. Earth supports complex life partly because it receives relatively concentrated energy from the sun and radiates energy back into space in a more dispersed form. Order can appear locally because the larger process still allows entropy to increase. This is one of the reasons the phrase, "everything tends toward disorder," is incomplete. The universe can create extraordinary structures while entropy increases. Stars form, galaxies develop, crystals grow, planets emerge, life evolves. None of these phenomena require entropy to reverse universally. Local structure can increase as long as the total thermodynamic accounting allows even greater entropy production elsewhere. So energy spreading does not mean that complexity must immediately disappear. In fact, energy flowing through a system can sometimes create complexity. A hurricane is an organized structure powered by differences in temperature. A star is a stable-looking sphere sustained for immense periods by the interaction of gravity, pressure, and nuclear reactions. Life is perhaps the most remarkable example of matter maintaining complex organization while energy continually passes through it. But none of these structures last forever. The hurricane eventually weakens. The star eventually changes as its available fuel is transformed. The organism eventually loses its ability to maintain itself. The gradients that support these systems cannot remain unchanged indefinitely. Energy continues to exist, but the conditions that made it useful evolve. And this is where the story begins to become cosmic. The universe today contains enormous differences. Stars burn against a cold background. Matter is concentrated into galaxies, stars, planets, and smaller structures. Black holes contain extraordinary concentrations of mass energy. Radiation travels through vast regions of space. These differences make events possible. But if energy continually spreads, what happens after enough time? What happens when stars have exhausted their usable fuel? What happens when temperature differences become smaller? What happens when matter has undergone every transformation available to it and energy has become distributed more evenly across the cosmos? The strange answer is that a universe can contain energy everywhere and yet have almost nothing left that can meaningfully happen. This possibility is sometimes associated with the heat death of the universe. The phrase sounds as though all energy disappears and everything becomes cold in an ordinary sense, but that is not really the idea. The deeper possibility is that the universe approaches a state of extremely high entropy, where useful differences have largely disappeared. Energy would not need to be gone. It would simply have nowhere useful left to flow. There would be no large temperature differences to exploit, no ordinary stars continuing to shine as they do today, and fewer remaining processes capable of extracting useful work from the available energy. The universe could become increasingly quiet not because it has run out of energy, but because the energy has become too evenly distributed to drive the kinds of transformations we recognize. This is a remarkable reversal of intuition. We usually imagine that a universe dies when its energy runs out. Physics suggests something stranger. A universe may become quiet while energy still exists. The problem is not necessarily absence, it is equilibrium. And this distinction between having energy and having usable energy will guide us deeper into the mystery, because the next question is unavoidable. If energy is constantly changing form and spreading through the universe, then what exactly is this thing we call energy in the first place? Is it something carried by particles? Is it stored inside matter? Does it exist independently? Or is energy only a number describing the state of something else? To understand where energy ultimately goes, we first have to understand what it actually is. We use the word energy constantly. We say that food gives us energy, that batteries store energy, that sunlight carries energy, and that stars release unimaginable amounts of it. The word is so familiar that it feels as though we already know what it means. Yet when we ask a more fundamental question, what is energy actually made of? The answer becomes strangely difficult. Energy is not a substance. There are no tiny particles of pure energy flowing through a wire like water through a pipe. A battery does not contain a hidden reservoir of glowing material that slowly drains away. When sunlight reaches Earth, photons carry energy, but the energy itself is not something sitting inside each photon like an object inside a box. Instead, energy is a property of physical systems. A moving object has kinetic energy because of its motion. A raised object can have gravitational potential energy because of its position within a gravitational system. A stretched spring stores energy because of the arrangement of its atoms and the forces between them. Molecules can contain chemical energy associated with their structure and interactions. Electromagnetic fields can carry energy through space. These examples look completely different, yet physics describes all of them using the same fundamental quantity. That is what makes energy so mysterious. Imagine holding a stone above the ground. While you hold it still, nothing appears to be happening. The stone is not moving, glowing, vibrating violently, or producing sound. Yet if you release it, the stone accelerates toward Earth. Its gravitational potential energy becomes kinetic energy. Where was that energy before you released it? It is tempting to imagine that it was stored somewhere inside the stone, but the energy depends on the relationship between the stone and Earth. Change their separation and the potential energy changes. The energy therefore cannot be understood simply as an ingredient hidden inside one object. The same problem appears with a stretched spring. Pull the spring apart and you must perform work. Release it and the spring moves. We say that potential energy was stored in the spring, which is useful language, but on a deeper level, the energy is connected to the physical configuration of the system and the interactions among its parts. Energy describes what a system can do as it changes. This becomes even stranger when we enter quantum physics. An electron bound inside an atom cannot possess just any arbitrary energy. It occupies allowed quantum states associated with particular energies. When the electron transitions between states, the atom can absorb or emit a photon whose energy corresponds to the difference between those states. The photon carries that energy away. But again, the photon is not made of energy. A photon is an excitation of the electromagnetic field. Its energy is related to its frequency. Higher frequency photons carry more energy than lower frequency photons. A radio photon and a gamma ray photon are both photons, but their energies can differ enormously because their frequencies differ enormously. This reveals something important. Energy is not a particular kind of object. Different physical things can possess it in different amounts. Matter also carries energy, even when it appears completely still. Einstein's famous relation between mass and energy tells us that mass corresponds to rest energy. A particle does not need to race through space or glow with heat to possess energy. Simply having mass means that a system has rest energy associated with it. This is why nuclear reactions can release such enormous amounts of energy. When atomic nuclei rearrange, the total mass of the final system can differ slightly from the mass associated with the original configuration. That difference corresponds to energy released into other forms, such as motion and radiation. Matter has not mysteriously been turned into a substance called energy. Rather, mass itself is one way energy appears in the physical description of a system. At deeper levels of modern physics, fields become central. The universe is filled with quantum fields. The electromagnetic field exists throughout space. Electron fields, quark fields, and other fundamental fields are part of our best descriptions of nature. What we call particles can be understood as excitations of these fields. These excitations possess energy. A photon is an excitation of the electromagnetic field carrying a particular amount of energy and momentum. An electron is associated with the electron field and has rest energy, kinetic energy, when moving relative to an observer, and potentially other forms of energy depending on its environment. Energy, therefore, seems less like a material ingredient and more like a universal property connecting different physical states. And this explains why it can move through such radically different forms without losing its identity in our equations. The energy released by nuclear fusion in the sun can eventually become electromagnetic radiation. That radiation can reach Earth and be absorbed by matter. It can become chemical energy in a plant, electrical activity in a nervous system, mechanical movement, and finally heat. Nothing material has remained unchanged through this entire journey. The particles are different. The locations are different. The physical processes are different. Yet, a conserved quantity links one stage to the next. Energy is that quantity. This is one reason physicists take conservation so seriously. If an experiment appears to lose energy, the missing amount may indicate that something has escaped unnoticed. A famous example appeared in radioactive beta decay. Measurements seemed to show that energy was missing from the process. Instead of abandoning conservation of energy, physicists proposed that an unseen particle might be carrying some of it away. That hypothetical particle became the neutrino. Neutrinos interact so weakly with ordinary matter that enormous numbers of them can pass through Earth without being detected. Yet their existence helped restore the energy balance of the process. Nature seemed to be keeping its books even when humans could not initially see how. But perhaps the most remarkable part of energy is its connection to time. In physics, conservation of energy is deeply related to the fact that the fundamental laws governing an isolated system do not depend on when we perform an experiment. If the same physical laws apply today, tomorrow, and billions of years from now, then under the appropriate conditions, a conserved quantity emerges. That quantity is energy. This connection comes from Noether's theorem, which links symmetries of nature to conservation laws. Rotational symmetry is connected with conservation of angular momentum. Spatial translation symmetry is connected with conservation of momentum. And time translation symmetry is connected with conservation of energy. Energy is therefore not simply something objects happen to possess. Its conservation reflects something about the structure of physical law itself. That makes the question, where does energy go, much more profound than it first appears. Energy can move between objects, fields, radiation, motion, mass, and heat, because all these different systems participate in the same underlying physical framework. But there is still a puzzle. If energy is so deeply conserved, why does it sometimes seem to disappear when we look at the universe on its largest scales? Light traveling across an expanding universe can be redshifted. As space expands, the wavelength of that light grows longer. A longer wavelength corresponds to a lower frequency, and a lower frequency means that each photon is measured to have less energy. A photon can begin its journey with one energy and arrive billions of years later with less. So where did the difference go? There is no obvious object that absorbed it. This is where our everyday understanding of energy begins to reach its limits. In the curved and evolving spacetime described by general relativity, energy conservation becomes more subtle than the simple accounting we use for a falling stone or a battery. Locally, conservation remains extraordinarily powerful, but defining a single total energy for the entire expanding universe is not always possible in the intuitive way we might expect. And suddenly the question has changed. We began by asking what energy is. We discovered that it is not a substance, not a hidden material, and not a particle. It is a fundamental quantity associated with physical systems and their transformations, deeply connected to the symmetry of time. But the universe itself is not a simple laboratory box. Space expands, space-time curves, photons stretch across cosmic distances. And when that happens, even the seemingly simple statement that energy can never disappear becomes far stranger than it first appeared. Imagine a photon leaving a distant galaxy billions of years ago. When its journey began, the universe was younger and smaller. The photon moved through intergalactic space while galaxies formed, stars were born and died, and the universe continued expanding around it. Eventually, after traveling for billions of years, the photon reaches a telescope on Earth. But something about it has changed. Its wavelength is longer than when it began its journey. Its frequency is lower. And because the energy of a photon depends on its frequency, the photon now carries less energy than it once did. This creates an uncomfortable question. Where did the missing energy go? If a photon loses energy by striking an atom, there is no mystery. The atom receives the energy. If light heats a surface, the energy becomes microscopic motion inside the material. If a solar panel absorbs sunlight, some of the energy becomes electrical energy. We can follow the transfer from one physical system into another. Cosmological redshift is different. The photon can lose energy while traveling through an expanding universe without another ordinary object receiving the difference. There is no invisible battery being charged somewhere behind it. The energy does not simply fall off the photon and remain floating at some point along its path. Instead, the puzzle forces us to reconsider what energy conservation actually means. In everyday physics, we usually imagine systems against a stable background. A ball falls through a gravitational field. A pendulum swings. A machine converts electrical energy into motion and heat. We can draw an imaginary boundary around the system and calculate the energy entering and leaving it. On those scales, conservation of energy works extraordinarily well. But the universe as a whole is not simply an enormous box sitting inside something larger. Space itself evolves. Distances between sufficiently distant galaxies increase as the universe expands. And according to general relativity, space and time are not passive backgrounds on which physics happens. Together, they form spacetime, whose geometry can change. Light traveling through that changing geometry behaves differently from light traveling through an ordinary laboratory. A photon has a wavelength. As the universe expands during the photon's journey, that wavelength can be stretched along with the cosmic expansion. This is cosmological redshift. Light that was once emitted at a shorter wavelength can eventually be observed at a much longer one. Because a photon's energy is proportional to its frequency, and frequency decreases as wavelength increases, the observed energy decreases as well. This effect is not merely theoretical. When astronomers observe very distant galaxies, their light is often strongly redshifted. Radiation from the early universe has been stretched even more dramatically. The cosmic microwave background that fills space today originated when the universe was far hotter. Cosmic expansion stretched that radiation to much longer wavelengths, leaving the faint microwave glow we observe now. So the energy of those photons changed. If we insist on imagining energy as a physical substance that must always be transferred from one container to another, this seems impossible. But energy was never a substance in the first place. It is a quantity defined within a physical description, and the way conserved quantities behave depends partly on the structure and symmetries of the spacetime in which we define them. Earlier, we encountered the connection between energy conservation and time translation symmetry. If the laws describing an isolated system remain unchanged as time passes, then energy conservation emerges through Noether's theorem. But an expanding universe introduces a complication. The geometry of the universe itself changes with cosmic time. The universe today is not geometrically identical to the universe billions of years ago. The scale separating distant regions has changed. The background through which the photon travels is evolving. Because of this, the simple global time symmetry required for an ordinary conserved total energy need not exist for the universe as a whole. Locally, however, physics remains well behaved. If two particles collide in a laboratory, energy and momentum are conserved. If an atom emits a photon, the energy change of the atom corresponds to the emitted radiation. If a photon is absorbed, its energy is transferred into the absorbing system. General relativity expresses local conservation through the conservation of energy and momentum. The strange part appears when we try to take the entire evolving cosmos and assign it one simple number called its total energy. Our everyday intuition expects that number to exist. Nature is not required to satisfy that intuition. This does not mean that energy conservation is wrong. It means that a principle that works beautifully in one setting can become more subtle when the setting itself becomes dynamic. There is another way to appreciate this. Imagine drawing two galaxies on the surface of an inflating balloon. As the balloon expands, the distance between the drawings increases even though neither drawing needs to crawl across the rubber. The analogy is imperfect because the universe is not literally a balloon expanding into an outside space, but it captures one useful idea. Cosmic expansion concerns the changing relationship between distances. Now imagine a wave traveling across that changing geometry. By the time the wave reaches its destination, the scale through which it has traveled has changed. Its wavelength can therefore be different from the wavelength it had when emitted. For light, that difference corresponds directly to energy. This creates one of the rare situations in physics where asking, "Where did the energy go?" may contain an assumption that does not apply globally in the way we expect. There may be no unique cosmic destination for the supposedly missing photon energy. The simple global bookkeeping picture is not generally available in an expanding spacetime, and yet from the perspective of an observer, the effect is completely real. A redshifted photon arrives with less energy than a corresponding higher frequency photon would have carried. A detector responds to the energy it receives now, not the energy the photon would have had billions of years earlier. The expansion of the universe has changed what arrives. This has enormous consequences when repeated across cosmic history. The universe contains vast amounts of radiation, and as the cosmos expands, freely traveling radiation becomes increasingly redshifted. Its wavelengths grow longer, and its characteristic energies become lower. The universe does not merely spread energy across larger distances. Expansion also changes the energy associated with cosmic radiation, as measured by observers moving with the expansion. This means that the future of energy is tied to the future of spacetime itself. As the universe becomes larger, galaxies that are not gravitationally bound to us can become increasingly distant. Radiation traveling across those distances can become more and more redshifted. Light that once carried substantial energy may eventually arrive at fantastically long wavelengths. The cosmos becomes darker, colder, and more dilute. But even here, the word cold can mislead us. The universe is not approaching some simple state where energy has vanished. Matter, radiation, fields, black holes, and other physical systems can continue carrying energy. The deeper transformation concerns how that energy is distributed and what processes remain possible. Once again, we encounter the difference between energy existing and energy being available to produce useful change. Stars concentrate energy and release it into their surroundings. Planets intercept some of that radiation. Life can temporarily exploit energy gradients. Machines can extract work from differences in temperature, pressure, chemical potential, or motion. But these differences do not remain forever. Stars eventually change. Radiation spreads. Temperatures evolve. The universe expands. Energy moves from concentrated forms into increasingly dispersed ones, while cosmic expansion adds another layer that cannot be understood using ordinary laboratory intuition alone. And so the simple childhood statement that energy can never be destroyed begins to reveal its true depth. Inside ordinary systems, it remains one of the most reliable principles we know. Yet, across the entire universe, we must be careful about what we mean by the total energy in the first place. The question is no longer simply where energy goes. It becomes a question about the geometry of spacetime, the meaning of conservation, and whether the universe itself can be treated as one ordinary closed system. And as we follow energy farther into the future, another mystery appears. If stars eventually stop shining, matter cools, radiation stretches, and usable differences gradually disappear. What happens to all the energy still contained within matter itself? Because even a perfectly motionless object contains an enormous amount of energy, and that energy is hidden in something we usually think of as completely different: mass. Place a stone on a table and leave it completely still. It produces no visible light. It makes no sound. It does not seem to be doing anything at all. Yet according to modern physics, that quiet piece of matter contains an extraordinary amount of energy, not because it is hot, moving, electrically charged, or about to fall, but simply because it has mass. This is the meaning hidden inside Einstein's famous equation, E equals mc squared. Mass and energy are not two entirely separate ingredients of nature. Mass contributes to the energy of a system. Even an object at rest has what physicists call rest energy. The factor connecting mass to rest energy is the speed of light squared, an enormous number. This means that even a relatively small amount of mass corresponds to a tremendous quantity of energy. 1 kilogram of mass, considered through this relationship, corresponds to roughly 90 quadrillion joules of rest energy. But this does not mean we can place a stone inside a machine and easily extract all of that energy. Most of the rest energy associated with ordinary matter is not freely available. Conservation laws and the structure of matter severely restrict which transformations can occur. Still, nature occasionally reveals just how real the connection is. Inside stars, atomic nuclei undergo fusion. Hydrogen nuclei ultimately contribute to the formation of helium, and the resulting system has slightly less mass than the corresponding starting components. The difference appears in other forms of energy. Some becomes motion of particles. Some eventually emerges as radiation. The sun shines because physical systems can rearrange themselves into configurations with different energies. This is often summarized by saying that mass is converted into energy, but that phrase can create the wrong mental picture. It sounds as though matter is one substance and energy is another, with nature somehow turning one into the other. The deeper description is more subtle. Mass is itself related to the total energy and structure of a system. Consider a proton. We often imagine it as a tiny solid object with a certain mass, but a proton is not a simple sphere. It is a complex quantum system involving quarks and gluons governed by the strong interaction. Surprisingly, most of the proton's mass does not come simply from adding together the intrinsic masses of its constituent quarks. Much of it is associated with the energy of the strongly interacting system itself. The motion and interactions of quarks and gluons contribute enormously to the proton's mass. Energy confined within the system appears, from the outside, as part of what we measure as mass. So when you hold an ordinary object, much of its mass ultimately reflects energy associated with microscopic fields, motion, interactions, and binding structures. Matter is not merely carrying energy. At a deep level, the distinction between matter and energy is less absolute than everyday experience suggests. This becomes even clearer when particles and antiparticles meet. An electron and a positron have equal masses and opposite electric charges. If they encounter one another under appropriate conditions, they can annihilate, producing photons. The original particles are gone, but their energy and momentum have not disappeared. They are carried away by the resulting radiation. The reverse can also occur under appropriate circumstances. Sufficiently energetic radiation interacting in the right environment can contribute to the creation of particle-antiparticle pairs. Again, it is tempting to say that energy became matter and matter became energy. But energy was present on both sides of the transformation. What changed was the form taken by the physical system. Particles can carry rest energy. Photons carry energy without having rest mass. The bookkeeping remains connected even as the objects involved change completely. This leads to an unusual way of thinking about the world around us. The chair beneath you, the ground below it, the atmosphere, your own body, and distant planets all contain enormous rest energy. The apparent solidity of matter hides a world of quantum fields and interactions whose energy contributes to the properties we associate with mass. And yet almost all of this remains inaccessible in ordinary life. A piece of wood can burn, but the chemical reaction releases only a tiny fraction of the energy represented by its total mass. The atoms rearrange their chemical bonds, while almost all of their rest mass remains essentially unchanged. Nuclear reactions reach deeper. They rearrange atomic nuclei, allowing larger changes in binding energy. This is why nuclear processes can release vastly more energy per unit of fuel than ordinary chemical reactions. But even nuclear fusion converts only a fraction of the relevant mass energy into forms that escape and can be used elsewhere. The rest remains within the products. So even when we speak of using energy, we are usually accessing only particular differences between physical states. This idea appears again and again. A battery does not provide energy because every atom inside it is being destroyed. It provides energy because chemical reactions allow the system to move toward a lower energy configuration while transferring energy elsewhere. A star does not shine because its matter simply disappears. Nuclear reactions allow its interior to move between configurations, releasing energy in the process. A falling stone releases gravitational potential energy because the configuration of the stone-Earth system changes. Useful energy often comes from differences between possible states. This is why an object can contain an enormous amount of rest energy while still appearing completely inert. The important question is not simply how much total energy exists. It is which transformations are physically available. The universe can contain immense energy without providing an easy way to extract it. And as time passes, this distinction becomes increasingly important. Stars spend billions of years transforming available nuclear fuel. Eventually, the conditions in their cores change. Depending on their mass, they may become white dwarfs, neutron stars, or collapse into black holes. The matter and energy have not vanished, but the opportunities for extracting energy from the system have changed dramatically. The same principle can be extended across cosmic history. The early universe was extraordinarily hot and dense. Matter and radiation interacted constantly. As the universe expanded and cooled, new structures became possible. Particles combined into nuclei. Electrons joined nuclei to form atoms. Gravity gathered matter into stars and galaxies. Stars created heavier elements and scattered some of them back into space. At every stage, energy changed form. Some became radiation. Some became motion. Some was associated with mass. Some became locked into structures that could remain stable for enormous spans of time. The universe we see today is, in a sense, a temporary arrangement of energy into countless different forms. But temporary may mean billions or trillions of years. A proton can remain stable for longer than any timescale we can directly observe. An electron, as far as we know, is stable. Matter can therefore preserve energy in remarkably persistent forms. Yet even stable matter does not exist in isolation. It sits within gravitational systems. It interacts with radiation. It can fall into stars or black holes. It can collide, bind, separate, heat, cool, and move. The energy associated with matter continues participating in the evolution of the universe. This raises a fascinating possibility. If energy can be carried by matter for extraordinary periods, perhaps matter acts as a kind of cosmic archive, not an archive containing readable memories, but a physical continuation of earlier events. The atoms in your body were assembled through a history stretching far beyond Earth. Many heavier elements were produced through astrophysical processes before the solar system existed. The material eventually became part of the cloud from which the sun and planets formed. The energy associated with that matter has passed through transformations older than our planet. Nothing about the matter around us is isolated from cosmic history, and the deeper we follow that history, the less meaningful it becomes to imagine energy as belonging permanently to any particular object. Energy can remain associated with one system for a time, then appear in another form after an interaction. A star releases photons. A planet absorbs them. Matter warms. Molecules move. Radiation escapes again. The carriers change while the physical accounting continues. But there is one object in the universe that seems capable of interrupting this story in a particularly dramatic way. A black hole can absorb matter and radiation alike. Once something crosses its event horizon, it can no longer return to the outside universe in the ordinary way. From our perspective, enormous amounts of mass energy can disappear behind a boundary from which even light cannot escape. And that creates the next question. If energy falls into a black hole, is it truly lost? Or does even the darkest object in the universe still have to keep track of everything that enters it? A black hole seems like the perfect place for energy to disappear. Anything that crosses its event horizon can no longer return to the outside universe in the ordinary sense. Light cannot escape. Matter cannot turn around and fly back out. If you dropped an object toward a black hole and waited long enough, it would become permanently hidden from distant observers. So what happens to its energy? Imagine sending a small object toward a black hole. The object has mass and therefore rest energy. It may also carry kinetic energy, electrical charge, and angular momentum. As it falls deeper into the gravitational field, its motion changes dramatically. Eventually, it crosses the event horizon. From far away, the object is gone from view, but its contribution to the physical system has not simply vanished. The black hole can become slightly more massive. This is one of the most important things to understand about black holes. They are not holes in the sense of empty gaps where physical quantities cease to exist. A black hole itself has measurable properties. From the outside, we can describe it through quantities including mass, electric charge, and angular momentum. If matter-carrying energy falls inward, the black hole can gain mass. If the incoming matter carries angular momentum, it can affect the black hole's rotation. The outside universe therefore retains information about certain overall properties of what entered, even though the detailed object itself becomes inaccessible. Energy has not escaped conservation simply by crossing the horizon. It has become part of the black hole. But black holes become much stranger when quantum physics enters the story. For many years, black holes were imagined as almost perfectly one-way objects. Things could fall in, but nothing could come out. If that were completely true, a black hole could continue accumulating energy indefinitely. Then Stephen Hawking discovered something remarkable. When quantum fields are considered around a black hole, the black hole is not completely black. It can emit thermal radiation. Today, this is known as Hawking radiation. The process is often described using a simplified picture in which pairs of particles appear near the event horizon, with one falling inward and the other escaping. That image can be useful for intuition, but the actual physics is more subtle. Hawking radiation arises from quantum fields in curved spacetime and from differences in how particle states are defined by different observers. The crucial result is easier to state. A black hole can lose energy. Because energy and mass are related, losing energy means the black hole's mass decreases. Over an extraordinarily long period, an isolated black hole can therefore shrink. For ordinary astrophysical black holes, This process is incredibly slow. Their temperatures are extremely low, and in the universe today, they can interact with surrounding radiation and matter. But in a sufficiently distant future, if the environment becomes cold and empty enough, Hawking radiation could dominate. The black hole would gradually evaporate. Something that once swallowed stars, planets, gas, photons, and perhaps enormous amounts of matter could eventually radiate its energy back into the universe. For a very long time, almost nothing appears to happen. Then, as the black hole becomes smaller, its temperature rises and evaporation accelerates. In the final stages, the remaining energy could be released increasingly rapidly. The exact details of the final moments require physics in regimes where our current theories are incomplete. But the broad picture produces a beautiful reversal. A black hole does not necessarily keep energy forever. Energy falls inward, contributes to the black hole's mass, and can eventually return to the surrounding universe in a radically different form. The original object, however, does not simply emerge again. If you threw a book into a black hole, Hawking radiation would not eventually produce the same book drifting back through space. The outgoing radiation would look thermal. The detailed structure of the original object would seem to have disappeared. And this leads directly to one of the deepest problems in theoretical physics, the black hole information problem. Energy conservation is not the only principle at stake. Quantum mechanics suggests that information about a physical state should not simply be destroyed. Yet, the traditional description of an evaporating black hole seemed to suggest that detailed information about everything that fell inside could disappear when the black hole itself vanished. This created a profound conflict between quantum theory and gravity. Modern ideas increasingly suggest that information is somehow preserved, although precisely how the full process works remains an active area of theoretical research. Black holes have therefore become laboratories for questions far deeper than whether matter can escape. They force us to ask what the universe is capable of forgetting. For our journey through energy, however, one lesson is already clear. Even the event horizon does not function as a place where energy simply stops existing. A star can collapse into a black hole. Radiation can fall into it. Matter can disappear from ordinary view. Yet the resulting black hole carries mass energy, influences space-time through gravity, and may eventually release energy through Hawking radiation. The form changes again. This pattern has followed us everywhere. The flame becomes radiation and heat. Motion becomes microscopic vibration. Mass participates in nuclear reactions and becomes radiation. Photons stretch across an expanding universe. Matter falls into black holes. Black holes themselves may eventually radiate. Every time we think we have found a final destination, physics reveals another transformation. There seems to be no simple graveyard where energy is collected after the universe has finished using it. Instead, there are physical states that can preserve energy for increasingly enormous periods of time. A black hole may survive for timescales so vast that the current age of the universe becomes almost insignificant by comparison. Large black holes can take fantastically long periods to evaporate. By then, the night sky would bear little resemblance to the one we know. Ordinary star formation may have ended. Many stars may already be dead. Galaxies beyond gravitationally bound regions may have disappeared beyond observable horizons because of cosmic expansion. The universe would be darker and more dilute. And still, energy would remain. Some could exist in low-energy radiation. Some could remain associated with particles or long-lived remnants. Some could remain locked within black holes until those black holes themselves slowly evaporated. But the important transformation is not simply the amount of energy. It is the disappearance of differences. Today, the universe contains enormous gradients. Stars are hot while surrounding space is cold. Matter is concentrated into structures. Radiation flows outward from luminous objects. These differences allow complex processes to occur. A planet can receive energetic sunlight and radiate lower energy infrared light. A heat engine can exploit a temperature difference. Life can use free energy gradients to maintain complex structures. But as energy spreads, those gradients become harder to maintain. A black hole may eventually return energy to the universe, but Hawking radiation does not reconstruct the stars and planets that once fell inside. Instead, it contributes to an increasingly diffuse background. Once again, conservation does not imply reversibility. This distinction is essential. The universe can preserve energy while losing the special arrangements that made that energy capable of producing familiar structures. A shattered glass still contains the same overall energy, accounting, as before the impact, once everything is included. But that does not cause the glass to rebuild itself. A dead star has not destroyed energy, but the organized process of stellar fusion that once produced its light has ended. A black hole may eventually release energy, but not as the intact worlds that crossed its horizon. Energy survives while structure changes. And as cosmic time stretches farther into the future, structure may become increasingly rare. This leads toward an almost paradoxical possibility. Perhaps the final state of the universe is not one in which everything has disappeared, but one in which almost nothing useful can happen. Energy could remain spread across enormous distances. Radiation could continue traveling. Particles might continue existing. Space itself could continue expanding. Yet the differences required for complex transformations could become vanishingly small. The universe would still contain physics. It would still contain energy. But it might contain fewer and fewer opportunities for anything new to occur. To understand how a universe full of energy can approach such profound stillness, we have to follow the story beyond stars and black holes and into timescales almost impossible to imagine. Because the ultimate fate of energy may not be destruction. It may be something much quieter, a universe in which energy remains everywhere, while almost every useful way of transforming it has disappeared. The universe today is filled with opportunities for energy to move. Stars burn because enormous differences exist between their interiors and the space surrounding them. Planets absorb radiation and release it again. Gas falls through gravitational fields. Matter collides, heats, cools, reacts, and reorganizes itself. Everywhere we look, energy is moving between forms because the universe has not yet reached equilibrium. But this cannot continue forever. Every ordinary star has a limited supply of usable nuclear fuel. The sun has already spent billions of years converting hydrogen into helium in its core, and although it has billions of years remaining, its current state is temporary. Eventually, the conditions inside it will change. Fusion will proceed through different stages. Its outer layers will expand and later be expelled, and the remaining core will become a white dwarf. Larger stars can end more violently. Some explode as supernovae, scattering newly formed elements through space. Their remnants may become neutron stars or black holes. Smaller stars can survive for extraordinary lengths of time, but even they cannot shine forever. The important point is that stars do not stop because energy has ceased to exist. They stop because the particular source of usable energy sustaining them changes or becomes unavailable. A star is possible because gravity compresses matter, and because nuclear reactions can occur under extreme conditions. It represents an enormous concentration of matter and a powerful flow of energy. Radiation leaves its surface and travels into colder surroundings. That temperature difference matters. The star is hot. The surrounding universe is much colder. Energy can therefore flow outward. This flow allows events to occur. It can warm planets, drive atmospheric systems, power chemistry, and in at least one known case support an entire biosphere. But once the star reaches the end of its active life, the flow changes. A white dwarf, for example, can remain hot after the star that created it has stopped ordinary fusion. It contains thermal energy and slowly radiates that energy into space. Given enough time, it cools. Nothing has stolen its energy. The energy has simply spread into the surrounding universe as radiation. Imagine extending this process not for billions of years, but for trillions. Stars continue forming as long as galaxies contain suitable gas. But each generation changes the available material. Some gas becomes locked inside long-lived stellar remnants. Some is ejected. Some may fall into black holes. The conditions required for widespread star formation gradually become less favorable. Eventually, the era of ordinary star formation is expected to end. The universe would not suddenly become completely dark. Long-lived stars and stellar remnants would persist. Gravitational interactions could still occur. Objects could collide. Black holes could continue absorbing matter. But the bright stellar universe we recognize would slowly fade. This future is difficult to imagine because almost everything in human experience happens during an extraordinarily active cosmic period. We live near a star that continuously floods Earth with usable energy. We see galaxies containing billions of stars. We look into the night sky and interpret points of light as permanent features. They are not permanent. They are temporary structures made possible by energy gradients. And this reveals something profound about the relationship between energy and time. The universe does not need to lose energy in order to lose activity. Suppose you had a perfectly insulated room containing one hot object and one cold object. Initially, the temperature difference could be used to perform work. You could place an idealized heat engine between them and extract some useful energy as heat flowed from hot to cold. Eventually, however, the two objects would approach the same temperature. The total energy in the room would still exist, but the useful difference would be gone. The room would have moved closer to thermal equilibrium. The distant future of the universe may resemble an unimaginably larger and more complicated version of this idea. Energy remains present, but gradients become increasingly difficult to find. Stars are among the most obvious gradients in the cosmos, so their disappearance represents an enormous change. Yet even after stars fade, gravity can continue creating events. Dead stellar remnants can orbit one another. Objects can occasionally collide. Some systems may slowly lose energy through gravitational radiation and merge. Matter can fall into black holes. Rare interactions can still release bursts of radiation. The universe does not become motionless the moment the last ordinary star stops shining. Instead, the pace of meaningful events becomes slower, and the timescales become almost impossible to comprehend. Human civilization has existed for only a tiny fraction of cosmic history. The universe itself is about 13.8 billion years old. Yet many discussions of the far future involve durations so enormous that billions of years become insignificant. The stars we see today belong to an early chapter. If the universe continues evolving for vastly longer than its current age, then the bright era of stars may represent only a small fraction of the full story. Afterward, remnants dominate. White dwarfs cool, neutron stars persist, black holes remain. Planets and smaller bodies may continue through darkness unless disturbed. The remaining energy becomes increasingly locked in forms that are difficult to access or spread through radiation, traveling across expanding space. This does not mean absolutely nothing happens. Given enough time, events that are fantastically rare on human timescales can become relevant. Gravitational encounters can rearrange systems. Objects can be ejected from galaxies. Remnants can merge. There are also questions whose answers depend on physics we have not yet fully established. One of the most important concerns, the proton. As far as experiments have shown, the proton is extraordinarily stable. We have never observed ordinary proton decay. Some speculative theories, beyond the standard model, allow protons to decay after immense periods, but this remains unconfirmed. If protons are truly stable, matter can persist in certain forms for astonishingly long times. If they eventually decay, then much ordinary matter could slowly transform into lighter particles and radiation. Either possibility changes the details of the far future, but the broader thermodynamic direction remains. Usable energy gradients tend to diminish. Even matter that survives does not automatically provide useful energy. A cold, isolated object floating through nearly empty space may contain enormous rest energy, while offering no practical mechanism for converting most of it into work. Again, the distinction returns. Energy exists. Available energy is something different. Eventually, black holes may become some of the largest remaining reservoirs of concentrated energy in the universe. They can survive for durations that dwarf stellar lifetimes. But as we saw, even black holes may not last forever. Through Hawking radiation, they can gradually lose mass. Over incomprehensibly long timescales, even enormous black holes could evaporate. Their energy would return to the universe primarily in increasingly diffuse forms of radiation and particles. After the last black holes are gone, the cosmos could enter a state unlike anything we can meaningfully compare with the present. No ordinary stars shining, no galaxies glowing as they do now, no large black holes remaining as concentrated reservoirs. Instead, an enormous, expanding universe containing extremely dilute particles and radiation. Energy would still exist, but it would be spread across extraordinary distances. This is the essence of what makes heat death such a strange possibility. The name sounds like everything freezes because the universe runs out of fuel. But the deeper idea is not simply that energy disappears. It is that the universe approaches a state in which there are fewer useful differences left to exploit. No hot star against cold space. No charged battery waiting to discharge. No concentrated fuel waiting to burn. No easy gradient from which complex processes can continuously extract work. The universe could contain energy almost everywhere while being unable to use most of it to create significant new structure. That may be the ultimate destination of the spreading we began with in a simple room. The candle burned. Its energy became heat and light. The heat spread. The light traveled outward. Scale that process upward, across stars and galaxies and unimaginable stretches of cosmic time, and a similar principle appears. Energy moves. Energy transforms. Energy disperses. The structures carrying it eventually change or disappear. And yet there is still one final mystery. If the universe approaches equilibrium and energy becomes increasingly spread out, does time itself continue to have the same meaning? After all, we recognize time partly because things change. Stars move, atoms interact, clocks tick, bodies age, radiation travels. But imagine a future in which meaningful changes become unimaginably rare. If almost nothing happens, what would distinguish one moment from the next? Energy has led us from a burning candle to the end of the stars. Now it leads us towards something even stranger, the possibility that the fate of energy and the meaning of time may be inseparable. Imagine waking in a room where everything is perfectly still. No clock is visible. No sunlight enters through a window. The temperature never changes. Nothing moves, decays, vibrates in any noticeable way, or leaves a trace of having changed. You wait for what feels like a moment, but there is nothing around you that distinguishes that moment from the one before it. Time may still exist in the equations describing this strange room, but without change, recognizing its passage becomes surprisingly difficult. In our universe, we experience time through change. A clock measures repeated physical processes. A heartbeat marks a sequence of biological events. Earth rotates. The moon moves through its orbit. Atoms oscillate. Light travels between places. Even our memories are physical structures created by processes that occurred earlier. Yet there is something peculiar about these changes. They seem to have a direction. We remember yesterday, but not tomorrow. A glass can fall from a table and shatter, but shattered pieces do not normally leap from the floor and rebuild themselves. A candle burns down, but does not collect its scattered heat and gases to become an untouched candle again. Physics calls this apparent direction the arrow of time. And surprisingly, energy alone does not explain it. Consider a video of two ideal billiard balls colliding. If friction and other complications are ignored, playing the video backward may still show a physically possible collision. The microscopic laws governing many physical processes do not contain an obvious instruction saying that one direction must be called the future. Yet the world around us clearly behaves differently. You can mix cream into coffee simply by stirring. Afterward, the cream does not spontaneously separate itself from the coffee and return to its original position. The difference is entropy. Before mixing, the cream and coffee occupy a relatively special arrangement. After mixing, their molecules can be arranged in an enormous number of ways while still appearing uniformly mixed. There are overwhelmingly more microscopic states corresponding to the mixed condition. So the system naturally evolves toward the condition with more possible microscopic arrangements. Entropy increases. This gives us a physical way to distinguish past from future. The past tends to contain lower entropy states, from which higher entropy states develop. The future lies in the direction in which entropy tends to increase. Energy conservation remains true throughout the process. The coffee does not lose energy simply because the cream mixes into it. What changes is the distribution of that energy and matter. This is why the arrow of time is closely connected to our question about where energy goes. Energy tends to spread, and as it spreads, entropy tends to increase. A hot object cools because energy moves into colder surroundings. Once equilibrium is reached, the energy remains present, but the original difference has disappeared. That process gives the event a direction. We can tell which state came first. If you watched a video showing a hot object spontaneously pulling random thermal energy from a room until it became much hotter while everything around it cooled, you would immediately suspect the footage had been reversed. The microscopic motions involved are not necessarily forbidden individually. The problem is probability. There are vastly more ways for energy to be spread among many particles than concentrated in exactly the right way to reverse a macroscopic event. For ordinary objects containing unimaginable numbers of particles, the probabilities become so extreme that the reverse process effectively never happens. This is why yesterday leaves traces. A footprint forms because pressure rearranges material. A photograph exists because photons trigger physical changes in a detector. A memory forms because activity in the brain changes physical structures and connections. Recording the past requires physical processes. Those processes consume usable energy and produce entropy. Even remembering has a thermodynamic context. This creates a fascinating connection between energy, entropy, and our experience of time. We do not merely live in a universe where clocks happen to move forward. We live inside a universe evolving from unusual lower entropy conditions toward higher entropy ones. But this immediately raises another mystery. Why was the early universe in a low entropy state at all? The young universe was extremely hot and dense, which might sound like maximum disorder. Yet gravity changes the picture. Matter was distributed remarkably smoothly across enormous scales. For a universe dominated by gravity, a smooth distribution can represent a state with relatively low gravitational entropy. Over time, gravity amplified small variations. Matter gathered into denser regions. Galaxies formed. Stars ignited. Black holes appeared. The universe developed structure while its overall entropy increased. This sounds contradictory only if entropy is treated as a simple synonym for visual messiness. A galaxy looks more organized than a smooth cloud, yet gravitational systems behave differently from the simple examples of gas spreading through a box. The growth of cosmic structure can occur while total entropy rises, and those structures create new energy gradients. Stars become extraordinarily hot compared with surrounding space. They release radiation outward. Planets intercept some of it. Chemistry becomes possible in environments far from equilibrium. On Earth, life exists inside this flow. We receive relatively concentrated energy from the sun and eventually return energy toward space in more dispersed forms. Between those stages, astonishing things can happen. Plants grow, atmospheres circulate, oceans move, animals think, civilizations build machines. All of these processes exist temporarily within a larger thermodynamic flow. This means that complexity does not contradict entropy. In some circumstances, flowing energy allows local complexity to develop, while the total entropy of the larger system continues increasing. But the gradients supporting that complexity are finite. The sun cannot shine forever. Earth cannot remain in its present condition forever. Stars throughout the universe cannot continually produce new sources of concentrated energy without limit. As the universe ages, more of its accessible energy can become dispersed, and the arrow of time continues pointing in that direction. Now imagine the process taken unimaginably far. Stars have vanished. Black holes have evaporated. Matter is extremely dilute. Radiation has been stretched to enormous wavelengths by cosmic expansion. Events still may occur, depending on the ultimate laws of physics. But the universe has moved far closer to equilibrium. What happens to the arrow of time then? The question is subtle. Time does not necessarily stop simply because the universe becomes quiet. The equations of physics do not require a ticking clock or a shining star for time to exist. But the physical differences that make the direction of time obvious could become increasingly difficult to find. Today, we distinguish past from future because irreversible-looking processes surround us. We watch things age, cool, break, decay, and disperse. In a universe extremely close to equilibrium, there would be far fewer dramatic transformations. One moment could resemble the next almost perfectly. Energy would still be present, but there would be little free energy available to produce complex events. This reveals something remarkable about our own existence. We live during an era when the universe is nowhere near complete equilibrium. There are stars in the sky. There are enormous temperature differences. There are atoms capable of forming complex molecules. There are planets receiving streams of radiation. There is enough usable energy for matter to organize temporarily into systems capable of observing the universe itself. We exist because energy has not finished spreading. Every thought you have occurs during this temporary cosmic imbalance. Every memory, every movement, every living cell, and every machine depends on energy flowing from one state toward another. If everything were already at perfect equilibrium, there would be no comparable gradients available to support processes like these. So perhaps asking where energy goes is also asking why anything happens at all. Energy does not merely power events. Its uneven distribution creates opportunities for events. The universe is active because differences still exist: hot and cold, dense and empty, high and low energy states, matter and radiation arranged far from equilibrium. And as those differences gradually change, they define the direction in which cosmic history unfolds. The arrow of time is therefore not a separate mystery floating above the physical universe. It is deeply connected to the way energy becomes distributed. The past contained gradients that the present has partially consumed. The present contains gradients that the future may consume. And far ahead lies the possibility of a universe in which almost every accessible difference has faded. Energy would not have disappeared. Time would not necessarily have ended. But the universe would have changed into something almost unrecognizable, a place where energy remains, while the opportunities for meaningful transformation have become extraordinarily rare. And that leaves one final question. If energy survives every transformation we have followed, from stars to photons, from matter to black holes, from concentrated heat to almost perfect equilibrium, can we truly say that energy lasts forever? Or does the expanding universe make even that question more complicated than it seems? We have followed energy through almost every kind of transformation the universe can offer. We have watched motion become heat, sunlight become chemistry, mass become radiation, and matter disappear behind the horizon of a black hole. We have imagined stars fading, black holes evaporating, and the cosmos approaching an increasingly quiet future. Through all of these changes, energy has seemed almost impossible to destroy. So it is tempting to reach a simple conclusion. Energy lasts forever. But physics rarely allows a statement this deep to remain completely simple. If we were discussing an isolated laboratory system in ordinary circumstances, conservation of energy would give us extraordinary confidence. We could measure the energy before an interaction, measure everything afterward, and expect the accounting to balance. If some energy appeared to be missing, our first suspicion would usually be that we had failed to detect where it went. This confidence has repeatedly helped physics discover things that were previously invisible. But the entire universe is different from a laboratory. There is no obvious wall around the cosmos. There is no external observer standing outside it, with an instrument measuring the total energy contained within. More importantly, the geometry of space-time itself changes. The universe expands. And because space-time is dynamic, the idea of one universally conserved total energy becomes much more subtle. Consider again a photon traveling through intergalactic space. As the universe expands, its wavelength becomes stretched. The photon is redshifted. Its frequency decreases, and therefore the energy associated with that photon decreases. We can measure the difference, but there is no simple object that receives the missing amount. This seems to contradict everything we have learned until we remember that conservation of energy is connected to symmetry in time. In systems where the relevant physical description does not change with time, a conserved energy can be defined in the familiar way. An expanding universe does not necessarily possess that same global symmetry. Space-time itself evolves, so the question, where did the photon's lost energy go, may not have the kind of answer we expect. It is not necessarily transferred into some hidden cosmic reservoir. Instead, the assumptions required for ordinary global energy conservation do not apply straightforwardly to the entire expanding universe. Locally, physics remains consistent. Atoms absorb and emit definite amounts of energy. Collisions conserve energy and momentum in their local interactions. Stars release energy through physical processes that can be carefully described. Nothing in your room suddenly violates conservation because the universe is expanding. The complication emerges only when we try to treat the whole cosmos as though it were one ordinary mechanical system. This distinction matters enormously when we ask whether energy lasts forever. Perhaps the better question is not whether some fixed cosmic quantity sits inside the universe for eternity. Perhaps we should ask what happens to the physical systems carrying energy as cosmic time continues. Imagine a photon emitted in the distant future. It enters increasingly empty space and travels while the universe expands. Its wavelength grows longer and longer. To observers moving with the cosmic expansion, its energy becomes smaller and smaller. It may never suddenly reach zero. Instead, it can approach ever lower energies as the wavelength becomes enormous. A universe filled with such radiation would still not be the same as a universe containing no energy at all, but the radiation would become extraordinarily weak and diffuse. Matter may also persist. If certain particles are perfectly stable, they could survive through enormous stretches of time. If protons eventually decay, then much ordinary matter may gradually transform into lighter particles and radiation. We do not currently know whether proton decay occurs. Black holes introduce another timescale. They can store enormous amounts of mass energy for periods vastly longer than the present age of the universe. Yet if Hawking radiation behaves as expected, even black holes eventually lose their mass and evaporate. After enough time, the universe could therefore contain fewer and fewer concentrated reservoirs of energy. Stars disappear. Warm objects cool. Matter may decay or become isolated. Black holes evaporate. Radiation stretches. The energy landscape becomes flatter. This is the key idea. The future universe does not necessarily become empty because energy is destroyed. It becomes increasingly unable to support large flows of usable energy because the differences that once drove those flows fade away. Think again about two containers of water, one hot and one cold. While the temperature difference exists, you can potentially extract useful work from the flow of heat between them. Eventually, they reach the same temperature. The molecules are still moving. Thermal energy still exists, but the useful gradient has disappeared. Now imagine that principle extended across the cosmos. Today, the universe contains spectacular inequalities. A star can have a surface thousands of degrees hotter than the darkness around it. The interior is hotter still. Matter is concentrated inside planets, stars, and galaxies, while enormous regions contain very little matter. Black holes create extreme gravitational environments. Chemical systems exist far from equilibrium. These differences allow the universe to remain active, but thermodynamic evolution gradually uses them. The universe does not consume energy as though it were fuel disappearing from a tank. It consumes differences. That may be the most important distinction in this entire story. When we say that a battery is empty, the atoms inside it have not lost all their energy. The battery still contains rest energy, thermal energy, and countless microscopic motions. What has largely disappeared is the particular chemical imbalance that allowed the battery to drive an electrical current. When a star exhausts its usable fuel, the energy of its matter has not vanished. The star has simply reached a state where the same energy-producing processes can no longer continue in the same way. When the universe approaches equilibrium, it does not need to become energyless. It becomes increasingly gradientless. And a universe without significant gradients is a universe with very little opportunity for complex change. There is something almost paradoxical about this. Energy may be everywhere, yet almost nothing can usefully happen. Radiation may cross space, yet there may be almost nothing left to absorb it. Particles may exist, yet be separated by extraordinary distances. Time may continue, yet meaningful events could become increasingly rare. The universe would still possess a physical state, but it would be very different from the energetic cosmos surrounding us today. This also changes the way we think about permanence. A star is temporary. A planet is temporary. A galaxy is temporary. Even black holes may be temporary. But the transformations connecting these structures can extend far beyond the lifetime of any individual object. The universe seems less like a collection of permanent things, and more like a continuous sequence of changing physical states. Energy provides part of the thread connecting them. The photon leaving a star may outlive the star that created it. The heat released by an event can spread long after the event itself has been forgotten. The mass of a collapsing object can become part of a black hole that survives for an almost incomprehensible duration. And the black hole may eventually release that energy again into a universe utterly unlike the one in which it formed. Nothing keeps its original identity forever. Yet transformations continue. So does energy last forever? Within ordinary physical systems, conservation gives us a remarkably powerful yes. Energy does not simply disappear during physical processes. For the universe as a whole, however, the answer requires more care. General relativity does not always provide a simple, globally conserved total energy for an evolving cosmos. That does not make conservation meaningless. It reveals that the concept of energy is more deeply tied to space-time than everyday intuition suggests. And perhaps that is the final lesson before we reach the end of our journey. Energy is not an immortal substance moving unchanged through eternity. It is part of the mathematical and physical structure through which we describe change. It appears in particles, in fields, in motion, in mass, in radiation, in heat, and in the relationships between physical systems. The forms can disappear. The structures can disappear. Even our simple idea of global conservation can become subtle when space-time itself evolves. Yet, at every scale accessible to ordinary experience, nature continues transforming one state into another with astonishing consistency. The candle does not erase its energy when the flame dies. The star does not erase its energy when it stops shining. And the universe does not simply throw energy away when familiar structures fade. Instead, the story moves toward its final and strangest possibility. Not a universe with nothing left, but a universe with energy still present and almost nowhere left for it to go. We began with a simple question. If energy can never truly be destroyed, where does it go? At first, the answer seemed easy. A candle burns and its chemical energy becomes light and heat. A moving object slows and its motion becomes microscopic vibration. A photon is absorbed and its energy becomes part of another physical system. Follow each transformation carefully enough, and the missing energy seems to reappear somewhere else. But as we followed that idea farther, the question became much deeper. Energy does not merely move between objects, it spreads. The warmth from the candle enters the room. The room releases radiation into its surroundings. That radiation can travel outward through space. Stars release energy accumulated through processes occurring deep within their interiors. Matter can fall into black holes, becoming part of their mass. Black holes themselves may eventually release energy through Hawking radiation. There is no single final container. No cosmic reservoir waits at the end of every transformation. Instead, energy participates in an enormous network of changes stretching across the history of the universe. And perhaps the most important thing we discovered is that conservation does not mean preservation of form. The flame can disappear completely. The candle can cease to exist in its original arrangement. The photons can be absorbed. The star can die. The planet can break apart. The black hole can evaporate. The structures vanish while the physical story continues. This distinction explains why the universe can age even if energy is conserved locally. A young star and an ancient stellar remnant may both contain energy, but they do not contain the same opportunities for change. A charged battery and a discharged battery both contain enormous amounts of rest energy, yet only one has the particular imbalance required to easily produce electrical work. The universe does not simply run on energy, it runs on differences in energy. A hot region beside a cold region creates an opportunity for heat to flow. Matter high in a gravitational field can fall. Chemical differences can drive reactions. Electric potentials can move charges. Stars can radiate into colder space. Wherever a useful difference exists, something can happen. And every time that difference is exploited, energy tends to become more dispersed. This is why entropy became unavoidable in our journey. Energy conservation tells us that the accounting remains consistent within the systems, where the conservation law applies in the familiar way. Entropy tells us why the transformations around us appear to have a direction. A shattered glass does not normally rebuild itself, and heat does not spontaneously gather from a cool room into one hot corner. Smoke does not naturally return to the exact shape of the object that produced it. Not because the energy required has vanished, but because the spread out arrangements are overwhelmingly more probable. The universe moves from special arrangements toward more probable ones. And we live during that movement. Everything familiar exists in the middle of this process. Stars have not all burned out. Matter has not reached complete equilibrium. Temperature differences remain enormous. Energy still flows through planets, atmospheres, oceans, organisms, and machines. Our own existence depends on this unfinished thermodynamic story. Every thought occurring in a brain requires physical processes. Every muscle movement requires chemical transformations. Every computer calculation ultimately consumes usable energy and releases more dispersed energy into its surroundings. Even asking where energy goes requires energy to flow. For a brief period in cosmic history, matter has organized itself into structures capable of wondering about the rules governing that flow. And yet the universe does not appear obligated to preserve those conditions forever. Stars will eventually stop shining in their present forms. Stellar remnants will cool. Black holes may slowly evaporate. Radiation will continue to travel through expanding space and become increasingly redshifted. The enormous gradients that make the present universe active may become increasingly rare. If this evolution continues towards something resembling heat death, the distant universe would not necessarily contain no energy. That is what makes the idea so strange. Energy could still exist in radiation, particles, fields, and whatever stable structures remain, but there could be almost no useful differences left. Imagine an ocean that is perfectly still and exactly the same temperature everywhere. The water has thermal energy. Its molecules continue moving microscopically, yet there is no temperature difference from which an engine could extract useful work. Now enlarge that idea until it encompasses the cosmos. The universe could become unimaginably large, dark, dilute, and quiet, while still containing physical energy. Nothing needs to switch the universe off. Nothing needs to remove the last unit of energy. The cosmos can become quiet simply because the energy has nowhere useful left to flow. This is perhaps the deepest answer to our original question. Where does energy go? Often, it goes everywhere. It leaves concentrated systems and becomes distributed among larger numbers of particles and fields. It passes from recognizable motion into microscopic motion, from stars into radiation, from matter into other particles, from black holes back toward the surrounding universe. Its journey is not toward a particular destination. It is toward different distributions. And over enormous periods, those distributions tend to become less useful for producing organized change. There is a quiet beauty in that idea. The light entering your room this evening may have begun inside a star millions or billions of years before reaching you. For a moment, some of its energy interacts with matter around you. It warms a surface or triggers a molecule in your eye. Then the journey continues. Heat spreads. Radiation leaves. Atoms move. Nothing holds the energy permanently. The universe is made not only of things, but of transformations between things. Objects seem permanent because human lives are short. A mountain appears eternal. A star appears fixed. Matter feels solid and enduring. But on sufficiently long timescales, almost everything becomes a process. Stars are processes, lasting billions of years. Galaxies evolve. Atoms can be rearranged. Black holes can change. Even space-time itself evolves as the universe expands. Energy links these changing states without needing to be a substance hidden beneath them. And this returns us to the deepest idea we encountered earlier. Conservation of energy is connected to symmetry in time. The fact that physical laws remain consistent as time passes is intimately related to the existence of energy as a conserved quantity under the appropriate conditions. Energy and time are therefore not merely two separate concepts that happen to appear together. They are woven into the structure of physical law. Perhaps this is why following energy eventually led us toward questions about the beginning and end of cosmic history. To ask where energy goes is to ask how physical states become other physical states. To ask how states change is to ask about time. And to ask why those transformations have a direction is to encounter entropy. The simple question opens into almost all of physics. So the next time you watch a flame disappear, listen to a sound fade, or feel a warm object slowly cool, remember that you are not watching energy vanish. You are watching a transformation. The organized becomes dispersed. The obvious becomes microscopic. The concentrated becomes spread across a larger world. And the universe quietly keeps evolving. Perhaps, unimaginably far in the future, the last bright structures will fade. The final great reservoirs of concentrated energy may disappear. Space may become darker than anything we can picture today. Yet the story will not end because someone removed the energy. It will become quiet because the differences that once allowed spectacular things to happen have faded. The universe may still contain energy. It may simply have almost nowhere left for that energy to go. And for now, we exist in the extraordinary interval before that silence. A universe filled with stars, motion, warmth, gradients, and change. An era in which energy is still finding new paths. An era in which the universe is still happening. And as you drift away from this question, perhaps towards sleep, remember that every transformation around you is part of that same enormous story. If you enjoyed exploring it with me, you can subscribe to Science Sleep Theory for more quiet journeys into the physics hidden beneath ordinary reality. Until next time, rest well, and let the universe continue its transformations around you.